Before we begin breaking down the hidden machinery inside activated carbon filtration, it is important to understand where this system actually sits inside the larger hydrogen ecosystem. What you are looking at is not a standalone filter. It is one of the most critical protection layers inside the entire green hydrogen infrastructure chain. At the far left side of the system, raw water enters the purification process. This water may come from municipal systems, rivers, wells, desalination facilities, or industrial process water streams. But regardless of the source, the water contains contaminants that can quietly damage electrolyzer membranes, poison catalysts, reduce efficiency, and shorten stack life. As the water flows through the purification chain, the activated carbon system sits at the center of the process. This stage removes chlorine, chloramines, organics, odors, and trace contaminants before the water moves deeper into advanced purification systems like reverse osmosis and deionization. This hidden protection layer quietly safeguards the entire hydrogen ecosystem behind the scenes. One of the most overlooked threats inside green hydrogen infrastructure is chlorine contamination. Most municipal water systems use chlorine or chloramines for disinfection. That makes the water safe for human consumption, but not safe for PEM electrolyzers. Even extremely small chlorine concentrations can quietly attack membranes and catalysts over time. Chlorine molecules enter untreated water streams and begin attacking sensitive electrolyzer components at the microscopic level. Chlorine is highly oxidative, meaning it slowly breaks down membrane structures while degrading precious catalyst materials. The result is lower efficiency, higher maintenance costs, reduced stack life, and eventually premature electrolyzer failure. This is why activated carbon becomes so important. Activated carbon acts as a chemical protection barrier, removing chlorine and oxidizing compounds before the water ever reaches the electrolyzer. What appears to be a simple filtration stage is actually protecting million-dollar hydrogen infrastructure from long-term chemical degradation. At the microscopic level, activated carbon itself is an incredibly engineered material. It contains millions of microscopic cavities and internal channels that create enormous surface area. Activated carbon works almost like a molecular sponge. As contaminated water flows into the carbon bed, contaminants begin interacting with the vast internal surface area hidden inside the carbon structure. 1 gram of activated carbon can contain a surface area approaching the size of a football field. That massive surface area creates countless microscopic adsorption sites capable of trapping contaminants. Chlorine molecules, chloramines, organics, odors, and trace impurities become attracted to the carbon surface and trapped inside the microscopic pores. Instead of continuing deeper into the hydrogen purification system, the contaminants remain locked inside the carbon structure, while only clean protected water exits the system. This adsorption process is one of the hidden molecular mechanisms quietly protecting hydrogen infrastructure every second during operation. At industrial scale, activated carbon filtration becomes a highly engineered infrastructure system designed to operate continuously under demanding conditions. Large stainless steel activated carbon vessels connect through extensive networks of industrial piping, pumps, valves, control systems, and instrumentation. These systems are engineered for reliability because the electrolyzer depends on them continuously. Pressure monitoring systems track operational conditions in real time. Automated valves regulate flow. Deep carbon beds maximize contact time between contaminants and carbon media. High-capacity vessels ensure stable long-term filtration performance. Most people focus only on the electrolyzer itself when discussing hydrogen systems. But the hydrogen economy depends heavily on hidden support infrastructure operating quietly behind the scenes. Without reliable purification systems like these, downstream membranes and catalysts would degrade far more rapidly, compromising both performance and economics. The activated carbon process itself follows a precise step-by-step purification sequence. Contaminated raw water enters the system carrying chlorine, chloramines, organics, odors, and trace contaminants. As the water flows into the activated carbon vessel, it moves downward through the carbon media bed. Inside the vessel, adsorption begins occurring continuously at the microscopic level. Contaminants become trapped within the porous carbon structure while purified water continues moving through the system. Once the contaminants are captured, clean protected water exits the vessel and continues toward downstream purification systems like reverse osmosis. This may appear visually simple, but this single purification stage has enormous consequences across the hydrogen ecosystem. By removing oxidizing contaminants early in the process, activated carbon helps extend membrane life, protect catalysts, reduce maintenance costs, improve operational reliability, and support long-term hydrogen production efficiency. But even activated carbon systems themselves require continuous maintenance and operational management. Over time, contaminants accumulate inside the carbon bed, gradually reducing adsorption efficiency and increasing pressure losses across the system. That is why industrial activated carbon systems require periodic backwash and regeneration cycles. During normal operation, water flows downward through the vessel while contaminants become trapped inside the carbon media. As contamination builds up, the system eventually initiates a backwash cycle. Water flow reverses direction and moves upward through the vessel at high velocity. This process lifts and expands the carbon bed, helping remove trapped contaminants and restore flow conditions. After backwashing, the system enters a rinse cycle before returning to service. Over longer operational periods, the activated carbon itself may require regeneration or replacement to restore adsorption capacity fully. This highlights a deeper reality about hydrogen infrastructure. Even the purification systems themselves require continuous monitoring, maintenance, and operational management to ensure long-term reliability. Activated carbon ultimately protects not just one machine, but the entire hydrogen infrastructure chain from water inlet to electrolyzer. Raw water enters carrying dissolved contaminants, including chlorine, chloramines, organics, odors, and trace impurities. The activated carbon filtration stage removes these contaminants before the water proceeds deeper into advanced purification systems. Clean protected water then continues through micron filtration, reverse osmosis, deionization, and polishing systems before finally reaching the PEM electrolyzer. Ultra-pure water then enters the electrolyzer itself, protecting membranes, catalysts, and internal components from chemical degradation. Reliability depends on the entire purification ecosystem operating together. A failure in one upstream protection layer can eventually trigger failures throughout the entire hydrogen plant. Activated carbon may appear to be just one filtration step, but in reality it acts as one of the primary chemical defense layers protecting the survivability of the entire hydrogen system. When viewed at full plant scale, activated carbon becomes part of a much larger industrial hydrogen ecosystem. Water intake systems, purification infrastructure, reverse osmosis, deionization, electrolyzers, hydrogen storage, and downstream industrial applications all operate together as one continuous process chain. Raw water enters the purification infrastructure before flowing through activated carbon filtration. This stage removes contaminants capable of damaging downstream systems while supporting long-term operational reliability. The purified water then continues through advanced purification processes before finally reaching the electrolyzer where hydrogen production begins. Clean hydrogen then exits the system and moves into storage, pipelines, or industrial applications. What this ultimately reveals is that hydrogen production depends on far more than electrolysis alone. Behind every kilogram of hydrogen is an entire hidden industrial ecosystem quietly managing chemistry, contamination, purification, automation, monitoring, reliability, and system protection. Activated carbon filtration may remain invisible to most people, but it quietly determines whether green hydrogen infrastructure survives long-term industrial operation.